Well, good afternoon, everybody. This is Roger Frechette with Interface Engineering. I wanted to say thank you to all of you for attending our webinar series today. And I would like to say we're very excited. This is the second installment of the Interface Engineering 2021 educational webinar series, which will run throughout the remainder of the spring and through the summer. Today's course on building design responses to mitigate virus threats for 2021 is an AIA accredited course. So when you registered, if you click the button, you will receive an AIA certificate. If you did not click the box and want one, no problem. Please just send us an email and we will make sure that you get your certificate for one learning unit. So I'd like to start out by introducing today's speaker, Mr. Joseph Diano. Joe is a professional licensed engineer. He is a LEED accredited professional, and he is an associate principal with us at Interface. Joe's role is as a mechanical discipline leader in the Washington, D.C. office. So Joe received his bachelor's degree and his master's degree from Pennsylvania State University. Joe is an expert in sustainable design and high performance design. And Joe has been responsible for the mechanical engineering on major projects across the United States and around the world. So without further ado, take it away, Joe.
Thank you so much, Roger, and good afternoon, everyone. Welcome. I guess it might be the first day of summer today based on how hot it is outside. As Roger mentioned, this is our second installment of many for this year, and we will be picking up where we left off last year. If you recall, some of you on the phone may have participated in last year's presentation that Roger and I did together, and this is really meant to be kind of an update to that, and where have we come in the past year and where are we going. So with that, I will get started and go through the course description. I won't read this whole thing. You can all read along, but essentially, what a year it's been. We've all been kind of adapting in real time to this sort of unprecedented situation. And now that we're seeing the vaccination effort accelerating across the U.S., the reopening, in quotes, of society is becoming a much more real thing to everyone. And so, leading up to this reopening, we've seen no limits to the amounts of information and guidance and recommendations that have been coming through. And it has been a challenge for everyone to sort of assess this mountain of data. So the idea of today's course is to kind of address the evolution of a lot of these mitigation and building readiness strategies. This course is designed for building owners, developers, architects, engineers, and really anyone else who's concerned with the impacts for buildings, building systems, and design decisions on the health and well-being of occupants. So the learning objectives for today are to try to gain a better understanding of how the SARS-CoV-2 virus can be spread within an occupied building and the different types of human exposure which can lead to infection. To discuss the importance of building systems evaluations to determine risk areas for buildings operating in epidemic conditions. To discuss specific strategies for current and post-epidemic conditions, and to discuss some of the specific technologies and componentry which can provide protection and reduce the risk of virus infections in both new and existing buildings. So I'd like to kind of start off with what I'm calling COVID-19, a brief history, and it's really just a timeline. It's been what many would consider to be a long year, and we've been operating in a certain mode for a while. So it's good to sort of take a look back of, where have we come from and where are we moving forward in the future. So, obviously we're all aware that in December of 2019, the virus was first identified, and then about a month later, the World Health Organization declared a public health emergency. The following day, the U.S. Health and Human Services declared a public health emergency in the United States. Within about a month and a half, the World Health Organization had declared COVID-19 to be a worldwide pandemic. And at that point, soon thereafter, about mid-March, many of us, started our working from home experience. Also of significance is, the ASHRAE Epidemic Task Force, which I will reference many times throughout this presentation. That task force was established at the end of March in 2020. And just the next day, Washington, D.C. had issued its first stay-at-home order. Many other states and jurisdictions had done so previously, and soon after that, a little bit tongue-in-cheek, but I think we've all experienced the great TP shortage that after the stay-at-home orders came through, became a real thing that we had to deal with. And then also to kind of put a date on it, the first Interface COVID-19 webinar was on May 27th of 2020. So where have we come since then? Roger and I were just chatting beforehand, and Operation Warp Speed came up. And this is something I think that doesn't get as much credit as maybe it should. Just 2 weeks prior to our previous presentation, Operation Warp Speed was announced. And when it was first announced, everyone thought this is great, but what a lofty goal, very ambitious what they were trying to accomplish. And I think by and large, it was a great success, because not just 7 months later, the Pfizer vaccine was given emergency use authorization by the Food and Drug Administration. And soon after that, the Moderna vaccine and then other vaccines followed. And so since that time, the data that I have here on screen is accurate as of yesterday. In the United States, over 232 million vaccine doses have been administered, and that represents at least 54% of the U.S. population over 18 years of age having received one dose. So, personally, I find that to be quite a remarkable achievement. But it's hard to talk about the history of COVID-19 without putting some of the other numbers that we've been seeing on a daily basis as a frame of reference. So at the time of our first webinar, there were a little under 2 million coronavirus cases, and we had just passed over the 100,000 death number in the United States. In the 335 days since that last webinar, the coronavirus cases are now approaching 33 million, which is almost 10% of the population of the United States. And the deaths are approaching 590,000. So I always look at these numbers because they give me pause, and they remind me sort of why are we still talking about this? Why is it important to talk about it? This has been a significant event in a lot of our lifetime. And, these numbers, while we've been seeing them day after day for a year now, you can become numb to them, but they're very important. So how has our thinking changed? There has been so much guidance that's been coming out, things that you see in the media, professional organizations providing guidance. It's been, at times very challenging to work through all of this information. And, you wouldn't be alone if at some point you have felt very confused or frustrated with some of the information that you're seeing. And one of the examples that I'll always sort of stuck out to me was specific to sanitizing your groceries. So on April 2nd of last year, news medias were reporting on, how to sanitize your groceries, because people were extremely concerned about this. We just didn't know what we were dealing with at the time. And this seemed to be, something that was very at the forefront. 3 weeks later, the same media outlets are reporting, no, there's no need to wipe down your groceries or your takeout, but you need to continue washing your hands. And so this is just one example of how quickly we were receiving information that sometimes contradicted itself. And it created this feeling amongst society as to, I don't. Forward a year later, this is a headline from just last week. The CDC advises that disinfecting surfaces to prevent COVID is often all for show. And so that kind of, to me encapsulates the types of things that have been happening over the course of the past year and that have left people wondering, am I doing the right thing? What is the right thing to do? ASHRAE has been taking a different tack in some cases, but also has been continually updating their information. So in April of last year, specific to airborne transmission of SARS-CoV-2, which we will get into a little bit more in the next section, they had put a statement out that said, transmission through the air is sufficiently likely that airborne exposure to the virus should be controlled. Just several weeks ago, they updated this guidance to say that airborne transmission of SARS-CoV-2 is significant and should be controlled. Changes the building operation including the operation of heating, ventilation, and air conditioning systems, can reduce airborne exposures. Now, while this seems like, from a sort of semantics, to be, not a big change, it's actually quite significant, because once they took the position that they feel like airborne transmission is sufficiently likely, that brought HVAC systems and the design of buildings and how we move air throughout a building even further into the forefront of what we're battling with. So I'd like to give a little bit of a refresher on sort of the virology behind COVID-19 and some of the modes of transmission. So the aforementioned contact transmission, which really is surface transmission, right? So you're touching a surface or shaking hands with someone who may be infected. This is also referred to sometimes as fomite transmission. This was at the onset something that everyone was, extremely worried about. So just on the 5th of April of this month, the CDC put out a statement stating that they believe the principal mode by which people are infected with the virus that causes COVID-19 is through exposure to respiratory droplets carrying infectious virus. And that while it's possible people can get affected through contact with contaminated surfaces, the risk is generally considered to be low. So again, while maybe some of us have thought this for a long time, it's actually very important when these entities, like the World Health Organization or the CDC, start to come out and make these statements, because it shows that our knowledge of this virus and how it gets transmitted is continuing to evolve, and we're getting more knowledge. And as we get more knowledge, that will inform better decisions. So the other two types of transmission are what is known as droplet transmission, which is, larger or smaller particles contained within, virus-containing respiratory droplets exhaled by an infectious person. Now, this is the type of transmission that is most likely to occur when someone is in fairly close proximity to the infected person, which is generally around 6 feet. And so that's where the 6-foot rule of social distancing is kind of, that's where it was born. Airborne transmission, however, is slightly different than droplet transmission. It's the transmission of infection spread through exposure to virus-containing respiratory droplets that are comprised of much, much smaller droplets. And these smaller droplets can remain suspended in the air over distances that are usually greater than 6 feet. And sometimes they can be suspended in the air for extended periods of time, up to hours. And so when you really start to think about airborne transmission as a potential path, or maybe even the most important path, you start to think about, air handling systems. How are we designing buildings? Because it becomes more important if you take airborne transmission seriously. Now, I will say that even as of today, there is still debate within the scientific and medical community about the significance of airborne transmission. The CDC and the World Health Organization, they acknowledge airborne transmission, but only for specific circumstances and specific settings. So they're really not, they're kind of acknowledging that it exists, but they're still stating, we don't think that this is the primary mode of transmission. ASHRAE has taken a different tact. And I think in many ways, it reflects the engineering background of ASHRAE, where as an engineer, we like to be conservative. We like to think not necessarily in terms of worst case scenario, but how can we be conservative in our analysis? And so they've taken the statement, or taken the position, as I mentioned before, that airborne transmission is significant and it is something that we need to control. There's been a lot of commentary recently in medical journals such as The Lancet and the Journal of the American Medical Association that are making arguments for the significance of airborne transmission. And I highlight these two articles because these two articles are from the past 2 weeks. So the information flow hasn't stopped, and I don't see it stopping for some time. We're going to continue learning more about this virus and how it spreads and how people get infected long after, the epidemic is over. So let's discuss some of the advancements in building readiness guidance. Last year at this time, I felt like there was a very large feeling of, what now? What do we do now? We're all working from home. We're thinking about, when are we going to get back to the office? If you're like me, perhaps you thought you would be getting back to the office much sooner than reality has sort of played out. And there was some confusion. There was a lot of information out there. The CDC is giving guidance. The World Health Organization is giving guidance. U.S. Health and Human Services is giving guidance. ASHRAE is starting to compile their information because, again, they're a leading resource in this field, and they have a lot of information and a lot of studies that have been done. But it was sometimes difficult to aggregate all the information, compare across sources to see what recommendations were. So in the past year, the ASHRAE Epidemic Task Force has really made great strides in trying to compile the most current guidance, the best information available, and make it available to the public. And so at the website that you see linked below, and don't worry about writing down that whole thing, because if you go to ashrae.org, it's very easy to get to the COVID information and to this infographic. And so they've started to compile all the resources in one place. And this has been really great, not only for those of us in the engineering community, but the community at large. It allows developers, building owners, maintenance professionals, architects, engineers. Everyone can go to one place and sort of see the information that is available to them. They have building guides that are broken down by building type. They talk about transportation industry. You can access a lot of the resources. You can access very specific data and comprehensive data, which I could spend 4 hours talking about the level of concentrated data for mitigation strategies, but I will hit sort of on a high level the ones that we find very important and that there's commonly questions asked. But one of the interesting things that the Building Readiness sort of program or idea has focused on is the systems analysis. And that's something that we at Interface, very quickly realized that, okay, as engineers, how do we start to combat this? Well, the first thing you need to do is define the problem. What is the problem? And so they've created or added some new terminology that I really like, that kind of highlights the different scenarios that we're going to find ourselves in both now and moving into the future. And that's epidemic conditions in place and post-epidemic conditions in place. But in either scenario, it all starts with a building systems evaluation. Now, sometimes when we think about these types of evaluations, we think, oh, this is just for existing buildings, but the same general strategies and ideas can be applied to new buildings as well. And going through this type of a systems analysis is really key to help identify what are the appropriate mitigation strategies for my building or my specific scenario, because there isn't really a one size fits all. And maybe not every mitigation strategy is going to be feasible. So it's very important to start with this sort of systems evaluation. So some of the key system evaluation components I'll go through now. It really starts with a detailed review of the building and the systems documentation. And that could be for a new drawing or a new building that's in design currently. It's a review of these design drawings. What are the HVAC strategies? What are the system types? What are we doing in this building? Are there things that we can build into the design now that will help address and mitigate some of these issues? And then for existing construction, do we have accurate record drawings that show everything that the HVAC system comprises of in great detail? Do we have testing and balancing reports, commissioning reports, BAS system trending? All of this information can be very important in assessing the current state of an existing building and how things are operating. But beyond just the document review, there's also an on-site component to this. And we have done dozens of these at this point in the DC office, and the same is true for engineering consulting firms throughout the country. I mean, this has been an effort industry-wide. So you got to get out there, you have to go to the site, you have to look at the equipment. Is it installed the way that it said it was installed on the drawings? Is it functioning appropriately? Has it been maintained? Are there any specific issues that need to be addressed before we move forward? These site visits help confirm what was on the drawings, and we can start to put information together about, air handling unit equipment and, what did the drawings say? What was installed? We can look at the BAS front ends when we're in the field and see how everything is operating. Is it operating in automatic mode? Is it in some sort of a manual mode? Gathering all this information is really important, because once we have all that information, we can identify anywhere there might be deficiencies in the existing systems and identify those for correction. Because really, before you start layering on any new or additional mitigation strategies, it is key to make sure that the building is actually working the way that it was designed. And then beyond that, once you have sort of remedied any deficiencies you found in the field, then you can start layering on the mitigation strategies. And so this is going to be specific for the building type, for the HVAC system type. You know, what are we going to suggest? Well, the suggestions are going to be different if you have a residential building that has individual split systems in every room versus a commercial building that is using a VAV system or potentially a dedicated outside air system with terminal units. There's different guidance for different types. And so once you've done the analysis, you can start to identify, okay, what is going to be the most appropriate? But it's also important to point out that this is not done in a vacuum. It's really critical that your client, when you're doing one of these assessments, is involved through every step of the process, because they may have specific needs or specific areas in their building that they're worried about, or certain operational restrictions that you need to keep in mind. Not every building is built equally. Not every building has the same level of maintenance staff. So these are things that need to be taken into consideration when you're thinking about these mitigation strategies. And then ultimately, at the end of the day, once you're done with the full analysis, it's really all about putting together what we call a building readiness plan. And this is something that is taking all of the information that you've been able to put together, all of the recommendations and strategies, and putting it in a simplified format so that the owners can understand what the roadmap is for their mitigation strategies. You know, what do we need to be doing? Who do we need to engage to get these things done? It can be very helpful to have this report at the end of the day, because it always gives something that you can go back to. So in addition to looking at, epidemic conditions in place, there's also the idea of the post-epidemic conditions in place. And really, this is after the stay-at-home orders have been lifted, after the move back into the office is becoming a real thing, and it's already a real thing for a lot of people. And moving forward, it's going to become a real thing to even more. There are people that are already back at the office. There are some that will be coming back in the summer, perhaps some after Labor Day. And it's important to sort of keep abreast of all the information, because things could change a lot 4 months from now. I think that's one thing we've learned over the past year, is that how quickly things can change is quite dramatic. And just yesterday, we received new guidance on if you're fully vaccinated, whether you have to wear a mask outside. It seems trivial, but we're going to keep getting more information like this, probably more rapidly, as we move forward. So the idea of post-epidemic conditions in place, it's to have a plan, right? If you're going to reopen a building, you need to have a plan. You need to be establishing communication with all of your tenants to verify what their needs are, when they're going to be back in the office, how often they're going to be back in the office, how many hours they're going to be operating. There's a lot of new criteria in the new world, or the new normal, if you will, than maybe were present previously. It's also important to confirm your supply chain, right? Maybe it's something that we didn't think about a lot in the past, but there have been shortages of materials as we've gone through the past year. So it's important, if you're running a building, do I have a good supply chain for getting filters when I need them, getting, any materials I may need to operate the building? Obviously, following local, state, and federal regulations, as well as CDC and OSHA guidelines, is important. As I mentioned, these guidelines are constantly being updated. So as industry professionals, it's sort of on all of us to try to stay abreast of these and make sure that we understand, what is the most current guidance, because this is information that's going to be changing rapidly, I would think, over the next several months. Engaging a mechanical service to complete necessary maintenance, also very important. Some buildings have been mostly dormant in this, last year or so. And so it's important to make sure, did we skip maintenance because people weren't here? Okay, we need to come in and we need to do all of that. Getting a commissioning provider or a tab firm or even a BAS contractor to verify that all the sensors and the bits and parts of your HVAC system are in working order. To review any of the BAS programming that has been done that may have been altered during epidemic conditions in place, that need to be reverted or changed in some way to allow for occupants to come into the building. And then finally, there's the ventilation and the plumbing flush. Once you know that everything is in working order, it needs to be turned on and it needs to operate for some period of time, typically days, to make sure that everything's working correctly and that you're flushing air through the building, you're removing any contaminants that may be in there. Same with plumbing systems that may have been dormant for some time, that you're circulating cold water and hot water through your building to make sure that things are ready when people come back into the office. So now let's get into some of the mitigation strategies. And I will caveat this with, this is not the panacea of every mitigation strategy, but I tried to highlight ones that are common and that are also generate a lot of questions as to, why this or why that. So we'll touch on a few of those now. This is a slide from last year that I actually kept in the new presentation because our thinking to the keys to mitigation really hasn't changed the interface. We targeted in on these 5 separate keys, and we think that, all of the guidance that's out there now and the mitigation strategies, they all fit into these buckets. So as long as you're thinking about, remove, neutralize, dilute, divert, defend, as long as you're thinking about those things as you're developing your mitigation strategies, you're going to be in good shape. So when we talk about remove, really we're talking about filtration predominantly. And so last year, ASHRAE had recommended that at a minimum that you provide, where possible, MERV 13 filtration. And if you can achieve MERV 14, that's even better. Well, since then, they have provided additional information to understand, how did they come up with that recommendation? And what they did is they took the best science that's available and they started applying it to the way that these different MERV ratings are achieved, right? So there's 3 different size ranges for capture efficiency, E1, E2, and E3. And they go from smaller to larger particle sizes. So what ASHRAE did is they looked at what they considered to be the anticipated distribution of the virus. They used historical information about viral things that we know about, like influenza, to figure out, okay, what droplet sizes are we actually going to be talking about in the air, and what fraction of those are there? So you can see, 20% at the smallest sizes and 51% distribution at the largest sizes. Then you look at the MERV ratings and figure out, okay, well, what are the different efficiencies of these MERV ratings? And you can start to see why the 13 minimum, 14 if you can do it, becomes important. Because at the smallest sizes, the E1 size range, when you go from a MERV 13 to a 14, you go from around 66% efficiency all the way up to 81%. So that's a big jump. And when we're talking about particles that may be suspended in the air, the smaller the particle size, the more likely that is. So it goes back to their idea of, airborne transmission is a significant pathway and we need to address it. And so they came up with what they called filter droplet nuclei efficiency. And that's taking all of this information, combining it together and saying, MERV 13 is great. You're around 90% efficiency. MERV 14 is even better. It gives you, almost 95% efficiency. And that becomes really important when you're talking about doing large air changes of within a space and doing a lot of filtration. At 95% efficiency, you can remove a lot of particles. So just a real quick refresher on filters in general. If you're not familiar with what a MERV 13 or 14 filter is, MERV 3, which is extremely low, it's something you might find in a window unit or a wall-mounted unit. MERV 8, which used to be the standard for office buildings, that is increased efficiency, but also is really just focusing on the very largest particle sizes, visible dust, things of that nature. MERV 13 is where you're starting to get into the droplet nuclei and virus capture. And then above that, you're really talking about Hepa filters. And Hepa filters are really a leap when you're talking from, MERV 13 or 14 to Hepa, because these filters, to be even considered Hepa, have to be 99.9% efficient at the 0.3 micron particle size, which is very, very small. And so you may be thinking, oh, this is great. Why don't we just put Hepa filters everywhere? Well, they can be quite a challenge in existing buildings to adapt your current filtration system to Hepa. And so we'll get into that a little bit more. One of the strategies we've looked at a lot for existing buildings has been electronic filtration. And what electronic filtration does is it replaces your traditional mechanical filtration, but it does so in a way that allows you to achieve comparable MERV ratings, 13 or greater, that you would have with the mechanical filtration, but do so in a way that produces less pressure drop. And that's important because in existing systems, you may not be able to swap out one filter for the other without having other negative impacts, whether that's impacts on airflow rates, impacts on static pressure. So electronic filtration has been something that has been, a key recommendation in many cases for existing buildings. There's also portable Hepa filtration. This comes up in a lot of areas, schools to be one, where you're concerned about a lobby maybe would be another. And these are, good strategies that can be applied where you're unable to do permanent filtration upgrades at the sort of HVAC system level. If it's not possible to do something at the air handling unit, can you do something for a specific space? It also offers a lot of flexibility. So if you have multiple spaces in a building that aren't going to be used all the time, it is possible to take your in-room filtration from one room into another, to sort of, follow where it needs to go with where people are in the building. Now, the one caveat I will give, and I have a lot of questions about this, is about these residential filtration units that are called HEPA. There really isn't any standardization in terms of requiring residential grade equipment to actually be certified as HEPA. So you will start to see some variations on naming, such as 99% HEPA, ultra HEPA. I've seen silent HEPA. They use the name, but you have to be a little bit wary because they may not always be true HEPA filtration. Really, for residential, you're looking at a different sort of rating system, which is called Clean Air Delivery Rate. I will say that system has its own problems, but when you're looking to compare one residential grade unit to the other, the higher the clean air delivery rate, typically the better. So now let's move on to sort of neutralization strategies. We discussed a lot about neutralization strategies previously. The first one I'll start with is UV, ultraviolet energy. This one has been around for quite some time. There is a decent amount of scientific data available for the effectiveness of UV systems. ASHRAE notes that these systems can be applied both in addition to mechanical filtration or potentially in scenarios where you're unable to do mechanical filtration. And essentially what these UVC systems are doing is targeting a specific wavelength that has been shown to be effective at neutralizing viruses, bacteria, and certain things that are in the air. There's surface UVGI, which we kind of mentioned before when we were talking about the whole idea of surface disinfection. These, when you're looking at sort of a commercial building or maybe the building types that we're looking at most frequently, aren't necessarily coming into play. However, they absolutely have their applications in healthcare situations where you're trying to truly sanitize an entire room. But really the applications that we've been seeing the most and having the most discussions about and getting the most questions about are these in-duct or in-air handling unit air disinfection systems. And essentially these are UVGI systems that are put into either some space that's available in an air handling unit or put directly into the duct to try to neutralize some of the virus particles that may be in the airstream. So you see here, these are a couple different examples of the tube type UVGI systems that can be placed in an air handling unit or in a duct. It's very important to understand that all of the technologies that we're talking about, especially with UV, are not necessarily a one-size-fits-all. There's a lot of criteria that goes into defining, how effective are these going to be. So here's an example of a UV system that is placed into a duct. You have to make assumptions about what is the velocity, this velocity at 500 feet per minute. That might be a velocity that you would find at an air handling unit. However, in some duct systems, you may have velocities that are much, much higher than that. And so then you have to start looking at the irradiation zone, right? And different levels of irradiance are going to be available from different UVC system types. So you have to look at, how much irradiance am I putting in? What is that irradiation zone? And you have to make these decisions because, in this example, we've shown an irradiation zone of 1 second. They can be shorter than that. They can be longer than that. In the case of, this example, you're looking at approximately 8 feet of straight length of duct that's required. So it's something that needs to be taken into consideration when you're thinking about using this on an existing system because you may not always have, that amount of space. Another type of UVC application is what is known as upper room disinfection. This is where actual UV fixtures are placed into a room to essentially irradiate the upper or unoccupied zone of space in the room. And the idea behind this system is that, as the dirty particles are being raised up to the higher portions and levels of the room, the UVC system is able to neutralize that and to mitigate that threat. This is something that you might see in large congregate settings, especially in medical applications. There are potential applications on the sort of commercial level, but it's not something we see as much, but it is an option that is available. Now, one of the other big items that has been a topic of conversation for some time and has been brought up a lot is bipolar ionization, or in this case, we'll talk about needlepoint bipolar ionization. And this is another sort of air neutralization and disinfection strategy where essentially you're creating positive and negative ions, and those ions will attach themselves to various volatile organic chemicals, germs, bacteria. In the case of viruses, they're meant to sort of neutralize and destroy the proteins that stick out of the membrane of the virus. And when it does that, it essentially renders it inert, because then that virus is not able to attach to anything and infect anything. There's a lot of different strategies for these, some of which are very similar to the UVC systems, with the one sort of item of note when it comes to the bipolar ionization systems is that they tend to be put into the supply side, because the delivery of the bipolar ions is really meant to be directly to the space. There's a lot of different equipment that's out there, comes in various sizes. You will see manufacturers stating that it can be placed in an air handling unit at very large volumes, all the way down to fan coil systems, even residential furnace systems, things of that nature. So there's a wide variety of applications for this technology, as well as the UVC technology as well. But the one key thing to note, and this was an item that has come up many, many times over the past year, is, do these pieces of equipment create ozone? You know, we've come a long way in our understanding of ozone, and now it is known that it can be harmful and it can have negative effects on human health. Early versions of bipolar ionization systems, and to some extent UV systems, were known to create ozone. And so as these systems came back to the forefront, people were very, very concerned. You know, am I going to be installing a system that is actually going to be harmful and not have positive benefits? So the guidance has been to sort of focus on the most current UL rating, which is UL 2998 for ozone-free validation. Once equipment has been validated to this standard, to the 2998 standard, it essentially is validated to not produce any ozone. So as you see these different products coming across, you know, your email or being suggested, you know, the recommendation is only use products that are UL 2998 validated. So now let's talk about some dilution strategies. This is kind of, you know, while it's a little bit out of order, this is sort of where we like to start in some cases, is to look at how much outside air can we bring into the space. And so the example we have on screen here is what we call the infection mode for an air handling unit that has an outside air economizer. And generally the idea is bring in as much outside air as possible to the occupied space to dilute any contaminants that may be in that space. You know, increasing at least to the minimum code required outside air is ASHRAE's recommendation, but they also recommend that you take it a step further and try to increase outside air. Well, how can we do that? Well, one way is to take a recirculating unit and make it 100% outside air unit by closing that return air damper and not allowing any air recirculation. Now, this may be appropriate for some equipment, but not all equipment, or potentially it's appropriate for certain outdoor air conditions, but not others. So this is where, you know, the previously mentioned system analysis becomes key, because you need to look at, in the case of an existing system or even a new system that's in design, what is it actually capable of? Not necessarily how do we want to normally operate it. So in some cases, you may have larger cooling coils, or the cooling coil has more capacity than it needs, so you can increase the amount of outside air. But all of these things need to be sort of worked in concert with the control system for the equipment, because at some point it may become too hot outside and you need to start recirculating some and backing off the outside air to maintain comfort conditions. So this is definitely a strategy to try to deliver more outside air to the space. Beyond that, you know, ASHRAE recommends when you're doing sort of building flushes and things of that nature, if you have operable windows and you can keep the operable windows open while you're running the HVAC system, you know, they recommend to do that, because again, it's just bringing more outside air and removing more contaminants in the space. Another thing that has come up quite a bit, and we see these dedicated outside air systems, you know, all over, whether it's in residential applications, commercial applications, etc. You know, dedicated outside air systems for the treatment of outside air have become quite common. And so while they're great, they're bringing in 100% outside air, they're already doing sort of that economizer function. There are specific components that you need to take sort of great care with and pay attention to. And in this case, specifically, the energy recovery wheels. We try to be energy conscious with the amount of energy we're using to condition outside air. And these energy recovery wheels allow us to recover a lot of energy from that exhaust airstream. But in the terms that we're dealing with now, which is, an epidemic conditions in place type scenario, you have to look at these wheels because in some cases they do bypass air from the exhaust airstream to the supply airstream. So we have been recommending in some cases that you turn the wheel off and you only operate it when essentially the system can no longer deliver the supply air set point temperature and humidity, because we don't want to unnecessarily burden the comfort conditions in the space by delivering extremely hot or extremely humid air. But on off-peak design, you may not need to operate that wheel, and you can still sort of supply the amount of air you need at the temperature and humidity that you need. And so you eliminate the potential for that cross-contamination. One of the other strategies we like to talk about is divert. And what does that really mean? Well, there's several different sort of regimes of airflow that we look at, one of which is pressurization and compartmentalization. And specifically when you're looking at, large applications for residential systems, right? What you don't want to have happen in a residential building is air that is in one dwelling unit somehow finding its way into adjacent dwelling units, right? Because then there's the potential that if there is airborne virus, that it could be transferred from one place to the other. So it's very important to look at these different building pressurization techniques, whether it's pressurizing a corridor so that the air that's inside of a unit stays in that unit and does not find its way out, or if you're looking at gym spaces in a residential building, or in general lobbies, things of that nature. It's very important to analyze these different pressure regimes to make sure that you have a system that is going to keep people as safe as is reasonable. One of the other systems that I like to discuss, we don't see a lot on sort of existing building retrofits because it's a little bit difficult to do, but on some of our new designs is displacement ventilation systems. So displacement ventilation differs from what what I would call traditional overhead ventilation in a few different ways, in that overhead ventilation is really what you would call a well-mixed model. You're mixing a lot of the air in the space to provide thermal comfort to the occupants in the space. While that's good for thermal comfort, it's not necessarily great for IAQ because you may have contaminants in the air that are being, mixed, and you're not getting rid of them quickly enough. With a displacement site system, if you have a large open area that isn't full of sort of, partitions or cubicle walls or things of that nature, where you can get good airflow into kind of the center of the space, the thermal plumes of the people or the computers in the space create a stratification that sort of lifts the contaminants and pollutions up out of the breathing zone into what, is referred to as the polluted mixing zone. And then once the contaminants are up there, you have high level return and exhaust grills that can then remove those contaminants. So it helps keep contaminants out of the breathing zone. And the effects of this can be seen in, the way that we calculate outside air requirements. So for this type of system, when you're doing your outside air totals via, standard 62 calculations, it actually gives you an air distribution effectiveness factor up to, around 1.2. So it's giving you kind of a 20% bonus because, it's been proven that these types of systems are better for indoor air quality. So finally, I'd like to discuss sort of the defend strategy. And while it may not be as, overt or, as technically complicated as some of the other, whether it's dilution or neutralization or filtration strategies, I feel that these are still important strategies because, it's been shown over the course of the last year that social distancing and staying away from people that are infected is an extremely effective way to help mitigate exposure to these, so to defend yourself from them. So, as the information comes from OSHA and from CDC about what are the guidelines for indoor activities, having signage and letting people know that these are the rules and this is what we're doing, it will help people safe. And you can't stress enough the importance of mask adoption. There's been, I won't get into, and that could be a whole 4-hour thing on its own, wearing masks, not wearing masks. It's been, quite the topic over the past year. But there is science out there, and it is, the science is showing that if two people are in an indoor space and they're wearing masks, you can significantly reduce the possibility of infection from one person to another. There are studies out there that are looking at the proportion of people that are wearing masks versus how effective the masks are. How many people need to be wearing masks because there is this efficiency to figure out what will lead to disease containment. And these are the types of scientific studies that are happening now. They're going to help inform our decisions moving forward. So hopefully there will be more and more information that comes out in the future. Touchless devices, again, while we're not as concerned about fomite transmission and surface transmission of COVID, touchless devices have always been and will continue to be a way to encourage sort of indoor occupant health by not having to touch surfaces and not having to spread germs around. So absolutely, these are still something that is important. And then just general healthy workplace strategies, whether it's a standing desk, encouraging people to walk around, eat healthy, these things are still important, right? And so we shouldn't forget about these sort of activities that help promote healthy workplaces as we move forward in the future. And lastly, I'd like to discuss some develops in scientific modeling. And sort of as an engineering nerd, this is the kind of stuff that I have been looking at a lot, and I'd love to see new papers that are coming out because, as an engineer, qualitative is great, quantitative information is awesome. And we're seeing now papers that are coming out where individuals are trying to put some metrics to what we know. In this case, it's a paper that's come out of MIT, Massachusetts Institute of Technology, and they're actually working on developing safety guidelines to limit indoor airborne transmission of COVID-19. So they're making an assumption that airborne transmission is something we need to be concerned about, and they're using the best scientific data that they have in the scientific method to come up with a way to make judgments based on science. And so what they're doing is they're modeling, various things such as what is the distribution of droplet radius sizes in terms of the volume fraction of air for different activities. You can see here they have singing softly, speaking, mouth breathing, nose breathing. They're using the science that's available to try to figure out, what is the flow regime coming out of an infected person and how can we model that? And so then they take that information to try to come up with what they're calling infection quanta, right? So they're, how infectious is the exhaled air? And again, I will caveat this that, I'm not stating that this is an absolute fact, but what they're doing is they're trying to come up with a metric that we can use, that everyone can use to figure out, how can we address these things? And what they're also doing is they're comparing it to situations that have already happened, various super spreader events where there was a chorus where many people were singing for many hours and a lot of people got infected. There were outbreaks on, the Diamond Princess on a bus in China. And so they're trying to look at scenarios where they have some information to see, can I fit our modeling with the data that we have to come up with a way that we can start to influence this criteria. And ultimately, this is what they're trying to put together. You can see two examples here, one for a classroom and one for a nursing home. And they're combining all of these different strategies and all of the different information and modeling to say what is safe potentially and what is unsafe, and to highlight the differences between, whether it's natural ventilation, whether it's mechanical ventilation, whether people are wearing masks, whether people are not wearing masks, to try to come up with some numbers to say, okay, if you're at this occupancy and this is the duration of time that you're going to be indoors inside this space and the mechanical system is doing this and people are doing that with wearing masks, how long can you stay in this space to be safe? So I find this very encouraging, and I think as we move forward, you're going to see more and more scientific data like this come out so that ultimately at some point in the future, we will have a better arsenal that we can work with and tools to work with to come up with, scientifically educated, ideas on how we can mitigate these things and what should the rules be. So in summary, again, I'd like to stress, and this is also a slide from the previous presentation that I thought was still wholly appropriate. There's no silver bullet. We have to work as a design community together to figure out what is the best for our buildings. How do we tailor these solutions for the building type, the space utilization, HVAC system types, operational constraints, things of that nature. But when you look at all of these different strategies that are out there, I feel like, we can do a lot. And, through the engineering community and HVAC design, there are a lot of things that we're able to do to help mitigate these issues. And I think as we move forward, the technology will get better, our understanding will get better, and ultimately the designs will be even safer for indoor occupants. So with that, I will open it up to questions. Let me open the little questions box here to see if there's anything in there. Oops, sorry, it's looking a little funky. I can see that there are questions, but I need to expand it quickly. Okay, here's one. How is increasing MERV ratings going to affect unit sizing, particularly in retrofits for office spaces? Could be cost prohibitive for many commercial building owners. So yes, that is absolutely a consideration that needs to be made. It could be cost prohibitive in some cases, but when we're looking at what I would consider to be standard design, which in the industry today, we do a lot of LEED buildings, and LEED was one of the first to come out and say, using MERV 13 filtration is a good thing. So if your standard design is assuming a MERV 13 filter, really going to MERV 14 can be, pretty achievable, I would say. Let me see. There are some other questions in here. It appears in my widget that was the only one. I apologize, Roger. If you're on there and you can see more than what I'm seeing here, please let me know. But that's the only one I can currently see.
Yeah, Joe, I think that's the one question that has been put in. Anybody can add questions onto the sidebar app if they'd like. I see. I think that's the one. But one question that I would have, Joe, is, or this is a question that I've heard from some building owners, is that there's this perception that we are in the final stages of COVID, and that things are getting better, and perhaps 6 months from now, we won't be talking as much about it. So for a building owner to make an investment now, are they wasting their money? Are these systems that are going to protect them against COVID going to be something that they may be criticized for having spent the money too late in the game? So how would you?
Right. No, I mean, I think that is a great question. It is something that's come up. Obviously there is a capital expenditure with any of these strategies, but I would say, if we've learned anything over the past year, our ability to predict the future and how things are going to go has not always been 100% accurate. Even now, the discussion about, various variants of, SARS-CoV-2 and the impact on those variants when it comes to the effectiveness of the current vaccines, we can hope, and I think we all hope, that the vaccines will be effective, but I think you have to plan for a certain level of resiliency when it comes to, this type of a pandemic situation. I mean, unfortunately, and perhaps I'm, more pessimistic than others, I don't see this being the only time that we will have to deal with this, possibly in my lifetime. And so I think it's important that we do as much as we can to help mitigate these strategies, but then also understand that, while we may be specifically talking about COVID and its impact, all of these strategies that we're talking about have tremendous health benefits and indoor air quality benefits beyond just COVID. So, a building owner or someone who's interested shouldn't think that, oh, if I put all this equipment in, it's really only addressing this one thing. And if this one thing isn't around anymore, did I waste my money? I would say no, because not only were you able to help mitigate virus effects, but you've also given a substantial increase to how good the indoor air quality is in your building. Okay, I see a couple other, or one other, about energy recovery wheels. Is it possible the energy recovery wheels will be removed as an energy recovery device altogether due to concerns about cross-contamination? That's a good question. I would say my personal opinion is no, only because I think what you will see is more attention paid to being able to bypass energy recovery wheels, potentially designing a system, sort of designing a system around it that does two things, that allows you to get the energy benefits of energy recovery when you can, but then when conditions are not really permissible for that type of operation, to bypass that wheel and keep the unit in operation. One of the things we don't want to forget about energy efficiency, although when you're talking about transmissions of viruses, energy efficiency is not always going to be the driving factor. I think what we're going to see in the industry is equipment just doing more than one thing, being able to operate in multiple schemes that are conducive to whatever the parameters are on the ground at that time. And with that, I think we are approaching the 1 o'clock hour, and I desperately didn't want to go over, so I'm glad it didn't go over. Roger, if you have any final comments you'd like to add, please feel free.
Yeah, thank you, Joe. Fantastic presentation. Thank you so much. I would just offer one observation, and that is, in talking to building owners, things are changing. Building owners want happy building occupants. They want happy tenants. And I think before, in the past, when a lot of the concerns or complaints may have had to do with thermal comfort or air movement in the space, suddenly I think all of us are a whole lot more interested in the quality of the air that we're breathing and the composition of that air. So although many of the strategies and technologies that you talked about today, Joe, have to do with mitigating this specific COVID-19 viral threat, I think what we're really talking about is a shift in the industry to be able to change the indoor environment to have better air quality for today and for tomorrow. So I thank you for the presentation, and I would also like to welcome everybody back in a couple of weeks' time. We will be having our third installment of the webinar series, where we will be offering a case study on a net zero energy campus that we had designed and built up in north of Pittsburgh, and that was for the Chatham University Edens Hall campus. So please keep an eye out for the invitation for that event, and we look forward to seeing you all at that time. Thank you so much, and have a great afternoon.
Have a great afternoon, everyone. Until next time.